All right, three, two, one. All right, let's get serious. All right. So, given a sequence, we define its sequence of partial sums to be the following sequence. Give me the original sequence, and I'll create a new one by adding up all of the terms. And that's it. That's the story. That's all it is. And the interesting thing, of course, with any sequence that we create, what we are interested in is whether or not it converges. So if the sequence of partial sums converges, then we write the limit as this fancy symbol, and we say that the series converges to whatever this limit may be. All right, so that's it. So this symbol means no more than just take the limit of this as n goes to infinity. No more, no less. That's it. All right. Now, that being said, this symbol has been historically very problematic in mathematics because everybody kind of forgets that it's a limit. And we will discuss that as we go throughout the notes here on series and talk about the various ins and outs. All right. Okay, so saying that this converges means that the limit of this exists. Saying this diverges means that this thing does not have a limit. It is a divergent sequence. All right. Okay, so that's all series are, right? Fundamentally, it is just I'm going to take the limit of these things as n goes to infinity. That's it. Now, the problem that the reason that a lot of mathematicians end up having issues with this is that they kept treating this thing right here as a summation, right? They looked at this as, oh, I add up terms infinitely many times, but it's really not what you do. What you really do is take a limit of a finite number of sums. And having that sort of wrong idea in your head causes some strange things, which we'll talk about and see. Oh, immediate cat attack. 2 minutes in, Olive shows up. All right, so that being said, now that we've sort of outlined what a series is, it's just a limit of these things. Our goal for this first video is to get a little sampling of how proofs with this stuff works, and fundamentally, we're going to also have to talk about how does this symbol really work. All right, how does sigma notation work? Right, so when I write this, of course, intuitively in our minds we think, x1 plus x2, all the way up to xn. But as we noted when we first defined this, it's actually sort of recursively defined, right? I tell you that the summation from 1 to 1 is just the first thing, and then if you want to compute the summation to n plus 1, well, then you compute the summation to n, and then add the n plus 1 term. So a lot of what we're going to do in this video and the next two for this week's wonderful topic on series, we'll first talk about how to prove some things involving the symbol, and then once we know how this works, then we'll take limits. All right, so let's begin with a very underrated technique, and that's the idea of telescoping. So, you probably saw this in Calc 2, and it was probably half of a day, if that, right? So if I give you a sequence, and I look at these sums, then this will always clean up into this. Okay. Now, if you write out the summation, you can kind of convince yourself it's true, right? Because you'll have x1 minus x2, plus x2 minus x3, plus x3 minus x4, all the way up. So everything cancels except for the first term and the last term. And the last one will be negative. Okay. So this, at first glance, may not seem like the most exciting result. Why is it called telescoping, you ask? Well, you can imagine like a telescope, like an old-timey one, right? It like is compact, and then you pull it out. So it's like this is the pulled out version, and this is the compact version of the summation. Um, but this is also a result in the vein of something that you see a lot, because the people that invented sigma notation hate it as much as you do, and will come up with all sorts of techniques to get rid of it. And that's really what telescoping is fundamentally about. It's how can I get a summation out of here. And that basic idea is very powerful because a lot of series, a lot of the limits that we're going to talk about, they're almost all boiled. They're boiled. They almost all boil down. That's what I was trying to say. They almost all boil down to, all right, how do I turn those partial sums into a simple expression that I can take the limit of? All right. And in terms of telescoping here, which we will prove, and note this is a for all n, so obviously we're going to do this inductively. This is an incredibly powerful technique, and in fact so powerful that I always learn something new about it. Every time I think about it and play around with it, I always cook up a new little thing, and I'm like, oh man, telescoping is super cool. In my own research, even, there are these things called Q algebras, and it turns out that a Q algebra is equivalent to some particular thing, and I couldn't find a reference. I couldn't find a proof. I just found everyone referencing it, like, "Oh yeah, this is true," and I couldn't figure out why it was true. And it turns out you had to use a telescoping trick like this, and I was very excited about that. But we'll also see a very cool telescoping trick today in this very video, one that I never knew of until I just, I was thinking about telescoping as I was typing this up, and then it dawned on me that, oh wait, you can use telescoping for this. I'm like, oh, this is the coolest technique. All right, so that being said, let's actually prove this wonderful technique. So it's an inductive proof, right? This is going to be true for all n. All right, so start with 1. I'll just plug 1 in. Boom, done. There we go. Yeah, it holds. Okay. The best, right? The best base case. I feel like there is an example. I can't think off the top of my head, but I know there's an example of an induction where like the base case is a complete nightmare, but then the induction hypothesis is super easy. I forget what that is. Oh, I know that exists. I remember having to deal with that once. But yeah, all right. So now, okay, let's suppose it works for m, and then we'll show it works for m plus 1. All right, well, peel off the m plus 1 term. And again, remember, this step right here is how the sigma notation is defined. Right, I just peel off a term. It's literally how it's defined, and by induction hypothesis, we know that this is equal to that. Oh, and lo and behold, those cancel, and we pick up the first term minus the last one. There we go. Since it's true for m, and we verified for m plus 1, and since it works for 1, it therefore works for all natural numbers. Beauty. Alright, nice. So, equipped with telescoping, we now give our example of a convergent series. So, we set up a definition. Given a sequence, you can create its series. So, the sequence 1 over n times n plus 1 is the sequence we're using. Then we look at its partial sums and take the limit. So we're demonstrating an example of a convergent one. We will get a divergent one in a little bit, but a convergent one for right now tells us that our definition, right, something satisfies it. So there you go. All right, and this is a classic one, and really is a good first series to prove converges to one. Converges at all. Right, because it's relatively simple. It turns out the most simple one has a bit of a problem. We'll get to that. But right, it's pretty straightforward and simple, and it converges to a number we like, 1. And the reason it converges is just simply from telescoping. The partial sums, so note the difference. They effectively look the same, but there's a key difference right there. And I also like to switch, when I'm dealing with the series, I use n, and for the partial sums, I'll use k. I think that visual change lets you really kind of, codify it. But, so this in here is equal to that. That is a partial fractions, which I am assuming that you're comfortable with. If not, you can just combine these two fractions as like that. All right, and then by telescoping, we know that, hey, this will give me the first term and the last term. And then, hey, the limit of this totally exists. The limit of that is just 1, because this will converge to 0. And so it follows that since the partial sums converge to 1, the series converges to 1. And there we go. Beautiful. Our very first series, rigorously proven. Cool. All right. There we go. Very nice. Okay. So let's keep going. So, like I said, kind of our goal is twofold here. We're not only going to talk about series and their various properties, we're also going to talk about how do you really work with sigma notation and how do you do proofs with sigma notation. So we will now prove a fact which is very clear, but again, needs a proof, which is if I multiply a summation, I can just distribute this throughout. So distributivity works if I add up a bunch of stuff. Right now, intuitively, we know that's true, but how would you write a proof? All right, well, let's do it. So again, it's going to be inductive. So we'll start off by noting, all right, if you replace this with 1, then the way sigma notation works, you just read it, and it goes, and that's it. So the more fun, the more interesting part is, of course, the induction hypothesis. So suppose that it was working for some m, and I want to show it works for m plus 1. All right. So again, remember the way this is defined, it's this plus the m plus 1 term. And now note, we have 1, 2, a sum, and then multiplying by r. So by our axioms of real numbers, we can distribute. So there we see distributivity coming into play. By induction hypothesis, I'm allowed to pull the r in here, and then now this is literally what this summation is. And that's that. Beautiful. So there you go. There is a nice rigorous proof verifying that if I sum up a bunch of stuff and then multiply by r, the r distributes the way you think it should. It multiplies everything. Now, an interesting thing, of course, would be to do this for a infinite version, so limits, but that's just going to follow from the fact that we can multiply limits and things work, so you can extend this to convergent series as well. Alright, but we did the finite case, and equipped with it, we will now prove a very cool formula, which is the following one. This formula is this formula is amazing. So I love this one, and this is one that you definitely encountered when you took Calc 2 and you talked about series, because obviously this one is hopefully ringing the alarm, because your brain's going, aha, geometric, I know where this is going. Right, but probably the way you were shown was a sort of, oh, you just multiply this across, and then you get this, and the r gets there, and then stuff cancels. But really, what's going on is telescoping. So this is actually telescoping in the size, and I never actually realized that that was what was going on with this until I was actually typing the notes for this, where I was like, oh wait, shit, this is telescoping. Right, because one of the tricks that you would do to do this proof is you do this times this minus this times this, and you sort of just draw it out and then you shift it and you cancel them out. But by general distributivity, we can bring this in, then you can pull this apart, and then now this is telescoping. First term minus the last term, there you go. Now note here, the summation starts at 0, and as I've already mentioned, it does not matter where these things start. You can start them at negative 15. So if you prove something starting at 1, it's true starting elsewhere, changing what needs to be changed. Mutatis mutandis. Whipping out the Latin. Show you, I got a PhD, all right? There you go. I said that to somebody once. We were talking about somebody, and they had a pierced septum. The thing that separates your nostrils. And I said it, and then somebody else said, you only said that because I said it. I did not hear them at all. And then I went, I've got a PhD. I know what a septum is. And, that's how you flex on people. My roommate in college was a wrestler, and he had a deviated septum, so, yeah. Anyway. Alright, so equipped with this, we now prove all-time classic, the geometric series. I should call this a geometric series. Why doesn't this have its name? I do not know. Where is it? Oh, there it is. Yeah, why am I not calling this geometric series? I don't know. I named everything else. Why didn't I name this? Alright, anyway. Alright, so here it is. Hey, there you go, the very famous geometric series. So if I have a real number that lives strictly between -1 and 1, then the series converges, and in fact, I have a very nice formula for the value. Beautiful. Alright, so that is the story of the geometric series. Okay. So, as we just saw with our first series that we showed converges to something, this one also has a pretty easy proof for convergence. We've already verified that since r minus 1 cannot equal 0, by the previous result, I know that this has to hold true. And then now, what else do we know? Hey, r is a number whose absolute value is less than 1. So when I take the limit, this will converge to 1 over 1 minus r, and the proof's over. Beautiful. The sequence of partial sums converges to what I claim it does. And again, be very aware that this only worked where r needing to be its absolute value strictly less than 1. If you start plugging in other values in this, you're going to start getting some weird stuff. And we'll talk about that in a little bit. All right. But there you go. So, geometric series in the bag. Nice solid proof. Beautiful. All right. So next up, our next goal is to talk about what I just said, which is it doesn't matter if this starts at 0, if this starts at 1. It turns out it does not matter, but we do want to prove that it does not matter in a very specific way. So that will give us a tool for manipulating series. All right, and by that I mean we're going to need to prove this little result here, which says that give me a sequence and give me natural numbers, so that n is strictly less than m. Then if I sum my way up to m, that's the same thing as summing my way up to n and then summing up the rest. Okay. So this is called general associativity because that's what this is really saying. This is saying that I can plop parentheses wherever I want. Right? M and n here don't matter, so no matter how much things I sum up and how little things I want to separate, I can separate them however I want. So I can place parentheses wherever I want, which is what associativity says. And again, this is inductive because our hypothesis guarantees that m is n plus j for some j. So that means what all you really need to verify is that if I replace m with n plus p, that works for any p. So that's how you turn this into an inductive argument. So note, good thing we proved that there's a way to connect the ordering of real numbers to the algebraic part of it, at least for the natural numbers, we have a tool for this. All right, so there you go. That shouldn't be too shocking that things like this are going to be inductive, right? Because I'm making a claim about an inductively defined thing. Proofs with this stuff should involve induction. All right. And this proof is, again, not going to be too bad because just look at your base case. That is literally how all this stuff is defined. There we go. One thing we didn't really talk about was the sum starting somewhere else, but as I know, if you want to get a little more formal in here, you can, but like I said, really doesn't matter where the sum begins. Okay, so the base case for 1 is just literally an unraveling of definitions. And now, suppose it's true for capital N. I want to show it's true for capital N plus 1. All right, well, if you add 1, you can peel off that term. Then we can apply the induction hypothesis. And then I can bring this term back into here. And there we go. So note, here to here, I'm actually using the associativity of real numbers because I'm moving these parentheses over to here and then combining them in the one term. So that's why this is called general associativity. Right, the name, again, like I said, it's saying that we can plot parentheses wherever we want in a summation, and here we see the actual axiom being used, which is good news. Alright, so again, I wanted to take the time to prove this, because we're going to explicitly use it to prove the following series fact. So, like I said, sort of the setup here for the series videos is going to be, let's prove something works for partial sums, and then talk about how it then comes up with limits. So if I have a series that converges, and I pick any natural number, then if I shift it up by n, that will converge to what you think it should, which is the original series minus off the things that we pushed ourselves past. So if you have something that converges, this is saying that you can peel terms off in the way that you think you should be able to peel terms off. Alright, and we'll do an explicit example of this in a moment, but let's get through the proof. The proof's very easy. Let S sub n be the partial sums for the original sequence. Let capital S be the partial sums where instead of starting at 1, we start at n plus 1. And so we'll do this whenever we have two series running around. I'll use a lowercase s and a capital S. General associativity, as we just proved, reveals that this plus this is equal to that. So this minus that is equal to this. So S sub n, capital S, which is that, is equal to this, which is little s minus that. Alright, so this is equal to that. This converges to the series. This is fixed. Right, remember, capital N is a fixed number, so this is just some real number. So when I take the limit here, the limit will exist, and the limit will go to where you think it should. So the limit of these partial sums converges to that. Beautiful. Alright, so like I said, the real power of this is the following. I can peel terms off of a conversion series in the way you think you should be able to. So, for example, the summation from 0 to infinity of 1 over 2 to the n, I can peel off the first term. This, we have the geometric series formula to give me 2, so I can subtract this over and then say to you that this summation is actually equal to 1. So this gives you ways of computing values of series by either taking terms off or putting terms in order to apply formulas that you know. Alright, and so note this allows you to peel off as many terms as you would like and go from there. So this is a technique that you definitely saw in Calc 2, and this seems at first glance a very just innocuous technique. This doesn't seem to be earth-shattering or groundbreaking, but you're going to be shocked where you'll use stuff like this. So in my research, in my chess namesake, Bishop's Lemma, Bishop's Lemma is, so quick side note on Bishop. So Eric Bishop is a mathematician who worked in analysis. So initially he worked in a branch of math called uniform algebras, which is where my research life began. He then wandered over into constructive analysis, which is a weird branch of mathematics. And along the way, he proved something that me and my colleagues call Bishop's Lemma. And something that I do a lot in my own research is make series, and I have to build series to do things that I want them to do, essentially. And in the proof of Bishop's Lemma, or at least the thing we call Bishop's Lemma, if you Google it, you get different things. There is a series trick. There is an amazing series trick. So the trick is as follows. 1 is equal to this sum. I can peel off n plus 1 terms, and then I peel off a term out of this, right, how this is, recursively defined, and then I subtract this over, so I get 1 minus 1 over 2 to the n plus 1 is equal to this. So it turns out that what we were doing, we were creating a series, and we needed the series to be less than 1, and what you can do is rework it to see that you've got the series of 1 over 2 to the n with the n plus 1 term missing. So, seems like a very basic idea, right? Just peel terms off, but note, you'll be surprised where little tricks like this will show up. So I remember the day I figured that out, and I showed my advisor, because we had a proof of it that one of our colleagues, Thomas Tonev, who is no longer with us, unfortunately, and my advisor was like, "Oh god, this proof Tonev wrote." And then when he was like, "Oh god, this step of the proof is a nightmare," and then I went, "Why? It's just this." And then I wrote this out, and he was like, "What?" It was a great moment with my advisor. He was like, "Wait a minute, what?" So the way Tonev had written it, it was not clear at all what the hell he was doing. But then I wrote it like this, and I'm like, "Oh yeah, this is what he's doing." And I was like, "Yeah, it's a fun little moment." But anyway, so basic series manipulation. This is something that people do. Right, so that's a good thing to connect it to. That, right, there is reason to study this stuff. Its limits, of course, So therefore they are interesting in their own right, but actually manipulating these sorts of things are things mathematicians have done for a very, very long time. But of course, we need to be careful with it. And that's going to be our final goal here for this video. Being careful. Because there is a very famous series that, oh boy, people got some weird opinions. But let's prove it. Okay. So, like we've been formatting, we're first going to prove something about summations, and then we'll see how limits come into play. Alright, so let n be a natural number that can be 0. So again, my notation for that is n sub naught. Okay, if n is even, then this summation is equal to 1. Right, and if you again think about what this would be, if it's 0, then it's negative 1 to the 0, which is 1. If it's 2, then we've got a 1 minus 1 and a plus 1, so 1. And likewise, if n is odd here, so for example, if n is 1, just think about writing it out. You'll have negative 1 to the 0, plus negative 1 to the 1, so you'll have 1 minus 1, which is 0. And hopefully the alarm bells are going off. We're going to take a limit and see that, well, actually you can. Alright, but again, let's actually prove this, and again, this will be inductive. So, as I already noted, for the first one, just plug in 0, you get 1. Now, suppose it's true for some even number, which is always of the form 2 times m. Then we want to show it works for 2 to the m plus 1. And now note here that this is 2m plus 2. So I actually have to peel off 2 things. Which, again, I'm allowed to do. That's just how it's inductively defined. And also, actually note, I'm technically also using general associativity here. Right? I'm peeling off the last... I'm slapping the parentheses where I want to. Alright, now by hypothesis, I know that is equal to 1, and then these terms are negative 1 and 1, and they cancel and I get 1. So, there you go. Doesn't matter what even number we add up to, it will always be 1. Beautiful. Now, note, right, you can intuitively figure out that that needs to be true, because if you're doing 1 minus 1 plus 1 minus 1, which is what we're writing here, right, if you're like, oh, if I stop after an even number of terms, right, I'll always have a 1 left over. And likewise, if I stop at an odd number, as we'll see, we'll get 0, because you'll have enough things that cancel. With an even number, there's always a leftover 1. With an odd number, there's always cancellation. Alright, and similar to point 1, we'll do this proof. So, again, pop in 1, that's equal to that. Suppose it's true for plus 1, any odd number, and then we'll go up here. So now note here, what we'll peel off is plus 2 and plus 3. This has to be 0 by the hypothesis. That has to be 1. This is an even number. This is an odd number. And that's the story. Nice and easy on the proofs there today. Hopefully, you think. Alright, so there we go. We've now verified that the partial sums of this behave in a very specific way, and that very specific way guarantees this divergence. So, we so far have only seen convergent series today. Let's wrap things up with a divergent one. Alright, so this is referred to as Grandi's series. It has other names too. Grandi was an Italian mathematician who was interested in series. And this one in particular tickled his fancy, and this one in particular, he was like the one who had like the right idea about this thing, which is, yeah, this just doesn't exist. And it's pretty easy to see why, because if you look at the partial sums, as we just proved, for even, we spit out 1, and for odd, we spit out 0. So this does not converge. Right? If this had a limit, it would have to get arbitrarily close to something, but the difference in the terms is always distance 1. So it never gets arbitrarily close. Now, of course, it's not a real proof. You'd have to actually, like, write out, like, there's a bad epsilon. Similar to how we proved negative 1 to the n's limit doesn't exist. You'd have to do this here, but same argument applies. Alright, so this is good news for us for a variety of reasons, because we've now proven that there are series that converge and there are series that don't, so figuring out when they converge and when they don't is a very worthwhile mathematical task. There are things that work and there are things that don't. So it's worth studying. Now, Grandi's series reveals the importance of being absolutely careful when you study series. Because if you treated this as a summation and not a limit, you would write something like this, and your lizard brain kicks in, and you go, ooh, parentheses, ooh, zeros, ooh, zero. Seems like that should hold. Right, but as we just verified, this is absolutely not true. Right, so this manipulation, which is completely valid for a finite number of terms, right, just placing parentheses wherever you want, generalized associativity, doesn't exactly carry over. Right, this grouping of terms is not allowed. You can totally do it with a finite sum, you cannot do it with an infinite. And because of this incredibly subtle nature of series, that while intuitively you should think of them as a summation of infinitely many things, this plus dot dot that you're doing here is really not valid. Because manipulating this as if this was an actual expression that could be manipulated leads you down a bad road. So, Grandi was really one of the first mathematicians to really start getting the ideas right and going, you got to be careful, right? And also, it's worth noting that I could have grouped the terms like this, and you would get 1 as the value of it. So it's clearly not something with a value. All right. And we need to be further careful because we do have a formula for geometric series, and if you look at this, this looks like geometric. It's a number to the nth power. And our boy Euler, was very adamant about this being true. Euler pointed out that for the geometric series, the summation, r to the n, he's like, we know what that's equal to. It's 1 over 1 minus r, so plug in negative 1, you get 1/2. That's what this thing has to equal. Right? Because as he pointed out, it's like, we know it lines up with it here, so there you go, that's what it's equal to. But that gives you all sorts of bizarre answers. So, for example, this would say that if you add up the powers of 2, you would get negative 1. You know, and it's like, what the what? That's no way that's true. But Euler was pretty adamant about this, which is an interesting thing. Like, he understood, like, he would concede that, like, this thing could have multiple values, or, like, there's something weird about this, but he was very adamant that its correct value was 1/2. So he sort of thought arguments like this were garbage, but he did them all the time, because mathematicians of the day were doing them all the time. But this was the one that he really thought, he's like, if this is going to have a value, it should be 1/2. And I'm calling this a blunder that Euler falls for. As you will do in your problem list number 3, it turns out he's not completely wrong. It turns out there's a way to make this equal 1/2. Or at least there's a way to meaningfully make it equal 1/2. With this idea of Cesaro summability. So that'll be something you'll do in your homework. And I hope you enjoy the proof of that one, because that proof's pretty neat. But yeah, there we go. Our first little sampling of series. So we've seen a couple of series that converge. We've seen one that diverge. We've got an idea of how proofs are going to work. So with that said, let's get going in the next video, where we're going to start getting into it.